Hello and welcome to Mathematics with Simon. I'm Simon and this is Chewy. We've been asked a question about Hero's formula, sometimes called Heron's formula, by Steve and Susan. And we love being asked questions. We want to be asked more questions. We like questions. Hero's formula. Given a triangle with sides A, B and C, apparently, according to Hero, who wrote a book at about 60 AD, ancient Greece, the area equals square root of s minus a, s minus b, s minus c, where s is the semi-perimeter, a plus b plus c over 2. So this is a very pretty formula, very symmetric formula. It's symmetric, so if we permute a, b and c, it stays the same. We're going to explore this formula, we're going to work out what's going on, we're going to prove it, we're going to do one proof. There are many proofs. Originally it was proved using a geometric method, as the ancient Greeks tended to. But we're going to use algebra. It's actually quite deep in mathematics. Most things that can be proved geometrically also have an algebraic proof and vice versa. But before that, we're just going to review what we know. So what we know is that for a triangle, the area is half base times height. Here's a rectangle. The area of the rectangle is the height times the base, and then the triangle takes up exactly half of that area by symmetry. I mean, this right angle triangle does, other triangles do too. It's pretty simple just to argue by symmetry that the triangle accounts for half of the area of the rectangle. So normal formula, the most commonly used formula for a triangle, area equals half base times height. So let's say if it was a 3, 4, 5 right angle triangle, the area would equal a half 4 times 3, which is a half of 12, which is 6. Let's use Hero's formula. So in this case, S would be a half of 3 plus 4 plus 5, a 12 over 2. S would be 6. So then we've got to work out square root of 6 times 6 minus 3 times 6 minus 4 times 6 minus 5. 6 times 3 times 2 times 1, square root of 36, which is also 6. That is a happy coincidence, happy result. So basically, it's just good to apply, just to make sure we understand it and see how it works, and it's reassuring we get the same answer with both formulae. Let's take another experiment. So here's a very thin isosceles triangle. The base is delta and the sides are just x. So we're going to assume that delta is absolutely tiny. That's what delta tends to represent in mathematics, very small numbers. So here the area is a half base, which is delta, times the height. And now x is very, very close to the height because delta is so tiny. So it's a half delta times x. We're going to say in the limit where delta tends to 0, x is the height. And then Hero's formula will say, well, s is 2x plus delta over 2, x plus delta over 2. And so the area is x plus delta over 2 times delta over 2 times delta over 2. In each case, we're taking x away from the semi-perimeter, times x minus delta over 2. This is the semi-perimeter with delta taken away. And basically what we're arguing is, well, these are about x. These are delta over 2. So it's delta over 2 squared. This is x squared. When you square root it, you get x times delta over 2, which is the same as we got with the other method. So that works too. It's nice to take limiting cases with these sort of things. It's just sometimes interesting, or it brings out certain characteristics of the method. Okay, so before we dive into this algebraic proof, we're going to remind ourselves that x squared minus y squared equals x minus y times x plus y. We will use this multiple times in the proof. I think maybe 4, but I'm not sure about that. We'll use it a lot. So let's start from what we know. So here's a triangle with sides A, B and C. This is a height. It's perpendicular to the base. So these are right angles here. That's what perpendicular means. And there's a side D here, there's a side E, and then D plus E equals C. So here the area equals the base, which is C, times the height over 2. So if we could work out H in terms of A, B and C, we would be well on the way to proving Hero's formula. So before we get H, we're going to get D. So by Pythagoras' theorem, we remember that a squared equals d squared plus h squared, and b squared equals e squared plus h squared. This means that a squared minus d squared equals b squared minus e squared equals h squared. They both equal h squared. If we rearrange, that tells us that d squared minus e squared equals a squared minus b squared. This is very useful, because by difference of two squares, d squared minus e squared equals d minus e times d plus e. And so that equals a squared plus b squared. Then we're going to divide through by d plus e. We're going to divide through by c. So d plus e drops out of the, because d plus e equals c. So d plus e drops out on the left, and then we're going to divide by c here. And now these two equations, we're going to add the equations. So we're going to add on the left hand side. So d plus d is 2d, minus e plus e cancels to nothing. So we've got 2d equals a squared minus b squared over c plus c. C is c squared over c, common denominator. So we get 2d equals c squared plus a squared minus b squared over c. Divide both sides by 2. D equals c squared plus a squared minus b squared over 2c. This is a major achievement, because what we've done is we've managed to express d in terms of a, b and c, which is one of the things we wanted to do. Next step, we're going to express h in terms of a, b and c. This is not too difficult, because h squared plus d squared equals a squared. So if we've got d, then h is the next step. H squared equals a squared minus, this is d squared. Again, we're going to stick it over a common denominator, which is 4c squared. So h squared is 4a squared c squared minus this stuff all over 4c squared. Now we're going to take square roots of both sides. So h equals the square root of all this stuff on the numerator over square root of 4c squared is just 2c. And that's given us h. And then to get to the area of the triangle, we're going to multiply by the base and then divide by 2. So multiply by c. The c's cancel. Then you've got 2 times 2 on the bottom, so you've got 4 on the bottom. Square root 2ac squared, I'm just reading it out, minus c squared plus a squared minus b squared squared. Okay, I have written 4a squared c squared as an exact square, 2ac squared. The reason is because then we recognise that this is the difference of two squares. That's so x squared minus y squared, 2ac is the x, and this business, c squared plus a squared minus b squared, is the y. Then basically what we're going to say is this is one side of the difference of two squares, and this is the other side. So this, if this was x squared minus y squared, then this is x minus y here, 2ac minus c squared minus a squared minus b squared, which is plus b squared. And this is x plus y. So 2ac plus c squared plus a squared minus b squared. Okay, and then we're going to realise we've got some exact squares in here. So a squared plus 2ac plus c squared is just a plus c all squared. So a plus c all squared here, minus b squared. And then in here, what we see is that a squared minus 2ac plus c squared is a minus c all squared. But all these three terms have got a minus sign, so it's actually right minus a minus c all squared. So that gives us a new way to write this. And then we realise we've got difference of two squares here and difference of two squares here. So again, we can factorise this as the difference of two squares. So this thing becomes this. Now this is looking a lot like Hero's formula now, isn't it? So we've got these four factors. This factorises the difference of two squares like this. A plus b minus c and minus a plus b plus c. Basically, let's look at exactly why, because b is playing the role of x, a minus c is playing the role of y. So if we've got x minus y, we've got b minus a minus minus c, which is plus c. And then when we've got x plus y, we've got b plus A minus C. Here, A plus C is playing the role of X and B is playing the role of Y. So we've got A plus C minus B and A plus C plus B. Okie doke. Now, next step, we're going to put this 4 inside the square root sign. So, the square root of 16 is 4. So if it's going to go inside the square root sign, it's got to go in as a 16, which gives us 4 2's, because 2 times 2 times 2 times 2 is 16. So we can give each of these 4 terms its own 2 in the denominator. And now all of a sudden we realise that A plus B plus C over 2 is the semi-perimeter. That's S. This is S minus B. This is S minus C. This is S minus A. It looks like this. S minus A, S minus C, S minus B times S. Change the order of the terms and we made it! Exclamation mark. The area is square root S, S minus A, S minus B, S minus C. Oh, I have enjoyed this so much, and so has Chewy. I usually give him a bit of something at the end of these, but I haven't got anything to give him. Where is he? Over there, passed out on the bed. It's been a hot day. I hope you've enjoyed this. I've enjoyed this. Please hit like if you have, and if you'd like to see more in the future, please hit subscribe and hit the notification bell. I love it when people ask questions and stuff, so please feel free to, if there's anything that interests you. Hope you're all well and look forward to seeing you soon.